All right, so we're working with our trig functions, and just like all the other functions that we've looked at, we need to know how to integrate them, we need to know how to differentiate them. So we'll obviously look at differentiation first, but in order to do that, need to define a few things. And I'm going to use limits here, because you'll remember from first principles, which I'll end up using, that all involves limits. If you think of your sine curve, it's very easy to work out the limit as x approaches 0. Just think of the curve. As the x value is approaching 0, that sine curve is also approaching 0. Cosine would approach 1, it goes up to the amplitude, and tan would also approach 0. Some of those will come in handy. Now I'm going to look at the area of sector AOC. Now this particular sector has a radius of 1, and we're just saying the angle at the centre is x. But what I do know is the area of that sector will be bigger than the triangle. It'll differ by whatever the area of that segment is. Now I'm going to create another triangle. If I draw in a tangent, which of course is perpendicular to the radius, so I create a right angled triangle. So OC extends, or is produced, to use the correct geometrical term. To meet AB, we get a right angled triangle. I could use trig, and we could work out AB would work out to be whatever the tan of x is. Because obviously opposite over adjacent, tan x over 1 would equal tan x. Okay, so I've got these three areas. Area of that triangle AOC, half AB sine, in this case, x. Area of the sector, half r squared, well, theta, in this case, x. And the right angle triangle would be half base times height. So just tidying that up, I can see that x is always in between sine x and tan x. Okay, going to divide all three by sine x. Now sine x on sine x, of course, is 1. Tan x on sine x, if you play around with the ratios, ends up being 1 on cos x. So I now have this idea that x on sine x is in between 1 and 1 on cos x. So again, if I look at what happens as x approaches 0, well, 1's a constant. Cos x, we said, approaches 1, so 1 on 1. I now know that x on sine x is in between 1 and 1. Well, that now tells me what that limit is. And that limit, the limit as x approaches 0 of x on sine x, becomes quite important in what we're about to do. Before I do use it to work out the derivative, just playing around with limits, because they do like to ask these sort of limit questions in extension 1. If I then had to find the limit as x approaches 0 of 5x on sine 5x, and what we know is the limit as sine x on x approaches 1, which also means x on sine x will approach 1 as well, because if you turn it upside down, 1 is still 1. And the trick is you've got to make sure the angle matches the other side of the fraction. Now you can't change the angle though. It's always the other side. In this case it's not a problem, they're both the same. So as long as they're the same, that'll equal 1. Okay? But if I get one where they're different, so as I say, I can't change the angle. So I've got to turn the x into a 3x. And we do that very simply by, okay, I'll change it into 3x, but then I'll have to multiply by a third as well. And then the limit of the 3x on the sine 3x, well, that's going to be 1. And so therefore the overall limit of this particular one then is a third times 1. So you make the angle and the other side of the fraction match. Okay, let's see how we differentiate sine x. Remember our first principles formula. The limit as h approaches 0 of sine x plus h minus sine x all over h. Going to expand out the sign. So sine, cos, cos, sine. If it's the sine, it's the sine. And I'm going to break this up in a very strange way. Because remember, the limit I know is that sine x on x. Or in this case, sine h on h is what I'm interested in. So I've got a sine h on h in that middle term. So I've put that by itself. So I know that limit will become 1. And so I'll get an answer of cos x. But what about the rest of it? I get this cos h minus 1 on h. And if I sub 0 into that one, it's not going to work, because cos of 0 is 1. 1 minus 1 gives me then 0 and 0. So I've got to play around with this cos h. So I'm going to use my double angle results. Remember, cos 2 theta, 2 cos squared theta minus 1. But in this case, h is double h on 2. So I get 2 cos squared h on 2 minus 1, but then minus the other one, I get minus 2. Okay? So that's all come from our double angle result. Now, cos squared minus 1 is the same as sine squared. So I can now rewrite the top of that fraction as 2 sine squared h on 2 on h. But remember, the angle has to match the other side. Oh, but it does, because I've got this 2 on h, which is the reciprocal of h on 2. But it's sine squared, it's not sine. It's not true to say the limit as h approaches 0 of sine squared x on x is 1. In fact, that limit would be 0. So I play around with this a bit more. Sine squared h on 2 on h on 2. And I split it up now to be sine h on 2 times sine h on 2 on h on 2. Because that's the limit I know. I know that's going to become 1. But as I said to you, the sine h on 2, that actually will become 0. So the whole limit is actually 0, not 1, when you have sine squared on top, rather than just sine. So I've ended up with cos x times 1. We know the limit sine h on h is 1. The other limit becomes 0. And there it finally is. The derivative of sine x is cosine x. Now, we don't obviously have to go through that process every single time. We can just say, well, we know the derivative of sine x is cosine x. In general, if you have the sine of some function of x, similar to what we did with exponentials, similar to what we did with logs, we differentiate the function and we'll place it out the front. So it'll be the derivative, the sine changes to cosine, the angle does not change. So that'll always be function x. Let's have a look at cosine x. I now know the derivative of sine x is cosine x. So what about cosine x? Well, if I rewrite the cosine as a sine function, because remember, they're complementary ratios. So I could say the sine of pi on 2 minus x. Remember, I've written pi on 2 there, not 90. Why? Remember back when we looked at the limits and created that limit? The angle was in radians. So whenever we're doing calculus with trig, the angle has to be radians for this to work. But we differentiate the angle, we'll get negative 1. So it becomes minus the cosine of pi on 2 minus x. But again, I'll use complementary ratios. And that becomes minus sine x. So sine goes to cosine, but cosine goes to negative sine. So in general, again, if we've got the cosine of some function, we'll differentiate the function, and then the cosine goes to negative sine. The angle does not change. Okay, let's have a look at tan. Tan I could rewrite as sine on cos. And so now I could use a quotient rule to work out the answer. So we'll square the bottom, that becomes cos squared x. Write down the bottom, cos x. Diff the top, well we just saw that when we differentiate sine x, we get cos x. Minus right down the top, sine x. Diff the bottom, and we just saw that when we differentiate cos x, we get minus sine x. So on the top, we end up with cos squared plus sine squared, which of course we know is equal to 1. And the reciprocal of cos is sec. So that's interesting. Well, differentiate tan, you actually get sec squared. In general, tan of some function, again, differentiate the angle. Tan goes to sec squared. The angle does not change. All right, let's do a whole heap of examples to reinforce this. So the sine of x cubed, we find the derivative of the function, that's 3x squared. The sine goes to cosine, the angle doesn't change. So 3x squared cos x cubed. Tan of 1 on x. Differentiate 1 on x, we get minus 1 on x squared. The tan goes to sec squared, angle doesn't change. So I've got minus 1 on x squared, sec squared, 1 on x. The log of cos x. Okay, this is actually a log function we're differentiating because we're saying the log of some function. Now the function happens to be a cosine function. Our rule for differentiating logs, we say, oh, that'll be the derivative on the function. The function in this case is cos x. So the derivative of cos x is minus sine x on the function cos x. So I get minus sine x on cos x, which of course we can simplify to be minus tan x. That'll come in handy later when we want to know how to integrate tan x, because we can then go back and say, oh, that must be minus the log of cos x. Tan to the power of 5. Remember, with trig, we don't normally write it in parentheses to a power. We put the power here, but this actually means tan x all to the power of 5. So we use our chain rule. Bring down the power and so on. So bring down the power, 5. Lower the power, so it now becomes tan 4x, or not tan 4x, tan to the power of 4x. Diff the inside. Well, the inside would be tan x. Differentiate tan x, we get sec squared. So 5, tan to the power of 4x, sec squared x. Ah, the swimming question. Cos e to the power of x. Now, we differentiate the function. The function is e to the x, world's easiest derivative. Differentiate e to the x, we get e to the x. Cos goes to minus sine, and the angle doesn't change. So it's minus e to the x, sine e to the x. Okay, let's play. And obviously in those exercises there'll be ones about looking at curves and tangents